Hey everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, maximum number of moves to kill all pawns. The number of solutions might look less, but I would say that the problem is not that difficult. My assumption is this kind of problems where two players are playing optimally for different goals is not common, and hence some contestants might have faced difficulty in approaching the problem itself. So in this video, we'll start with a simpler version of the problem and then build on top of it to solve the original problem itself. So that let's get started. The problem states that you're given a 50 cross 50 chessboard with one knight and some pawns on it. You are given two integers kx and ky, which denotes the position of the knight on the board, and a 2D integer positions where each position will denote the position of a particular pawn. Now Alice and Bob are trying to play a game where Alice will go first, and in each player turn, the following will happen. The player will select a pawn that still exists on the board and captures it with the knight in the fewest possible moves. Now, in this process of capturing the selected pawn, knight might go to a position which has some other pawn on the board, but at that particular move only one pawn can be captured, and that to the selected one. So if there are other pawns which knight has to pass through, it's completely fine. Those pawn will not be affected for this particular move. So in a single move, one pawn will be captured, and then the player's turn would change. So Alice will capture a pawn, and then Bob will capture the next pawn, then Alice will capture the next pawn, and so on and so forth. Now Alice's goal is to maximize the number of moves made by the both players during the entire game, whereas Bob's tries to minimize the number of moves made by both players. Now, assuming both players play optimally, as in if there is a chance which Alice can do, which in future will result in more number of moves, Alice will make that choice rather than making a non-optimal choice. Similarly, if it is Bob's turn and there's a turn or there's a move that Bob can make which will in future minimize the number of moves, then Bob will make that now instead of making a non-optimal move right now. So both the players are playing optimally, and given both the players are playing optimally, we need to return what is the maximum number of moves that can be achieved in the game, because Alice is the one which is starting the game, and Alice's goal is to maximize the number of moves, right? So let's take an example. Let's say knight is at 1,1 and there's just one pawn 0,0. So this is Alice move, and note that there's just one pawn, so Alice can just kill that particular pawn only. So Alice will try to kill that pawn, and there is in less than 4 moves you can't capture this pawn, and hence the answer here is 4. So in this 4 moves, Alice will capture the pawn and the game will end. Note that it may be possible that you can just keep move knight back and forth and not capture the pawn. In that case, you will increase your number of moves to capture the pawn or total moves played during the game. But as mentioned in the problem statement, once you select a pawn, that pawn should be captured in the minimum number of moves. So it should not be the case that Alice just moves the knight to a particular cell and then come back to the previous cell and keep doing this forever. So because Alice select this pawn, this has to be captured in the minimum possible moves, and there's no way to capture this pawn in less than 4 moves, and answer here is 4. Let's take one more example. Let's say there are 3 pawns in total, 1 1, 2 2, 3 3, and there's one knight which is at 0,2. So this knight, the turn is Alice. Alice can either capture this or this. But the thing is, if Alice capture 1 1 or 3 3, the total number of moves that will be played in the future will be lesser, and Alice know about it, and hence Alice plays 2 2, or rather Alice tries to capture 2 2 first and then give the board to Bob. And Bob knows that if he captured this one 1,1, the next time Alice will make the move, the number of moves will increase. So instead, let me capture this 3-3 first and let Alice capture the remaining one. So both of them are playing optimally, and if they do so, there can be at max 8 number of moves that can be played during the entire game, and hence the answer here is 8. So let's simplify the problem. Let's say both Alice and Bob are playing optimally, that's fine, but they are moving towards the same goal. That is, Alice is trying to maximize the total number of moves made during the entire game, and Bob is also trying to maximize the number of moves made during the entire game. Let's not, both of them are not fighting against each other. Let's say they both are driving the same goal. So what to do in this situation? If you haven't thought about this version of the problem, would encourage you to pause and try to think for a moment. So let's say you have a board with this particular knight and 4 pawns p1, p2, p3 and p4. Now what, this is Alice's turn, right? Now Alice has to make an optimal move, right? What does it mean? It means that if Alice is capturing something, Alice has thought about all other possibilities, and that is the best possible capture at this particular state, right? So what are the possible captures? Either Alice can capture p1, p2, p3 or p4. So if Alice captures p1, this is the board state that Bob will get, right? If Alice captures p2, this is the board state that Bob will get. And similarly, for if she captures p3 or p4, these two are the board state that Bob will receive. Now to get the optimal choice, Alice now need to understand that okay, what is the optimal number of moves, or what is the maximum number of moves that can be played using this board state, right? And let's say you got this number. So once you get this number and you just made 2 moves, like you can just, let's say you want to capture p1, so there is in just 2 moves you can capture p1 through this route, or in the right side as well, either going here as well. So in just 2 moves you will capture p1. So, and let's say you require some x1 number of moves, or x1 number of moves are optimal moves after this board state. So overall number of moves is 2 plus x1 if Alice decides to capture this pawn. Similarly, if Alice knows what is the total number of moves in this state, let's say 2 plus x2, 2 plus x3, 1 plus x4, Alice can simply understand which one of them is giving me the maximum number of moves, and Alice will make that move. So for this to happen, you need to solve for this x1, x2, x3 or x4. Rather, what you need to find out, given this board state, what is the optimal number of moves that can be feasible given Bob, it is Bob's turn. Because Alice and Bob both are driving toward the same goal, Bob's intention is also to maximize the number of moves that can be played. So again, Bob will play such that the total number of moves can be maximized. So what is Bob trying to do? Bob is saying that, okay, given this board state, what is the maximum number of moves I can achieve? Isn't this problem exactly equal to the original problem? The original problem was, given this board state, give me the maximum number of moves I can make at this particular state. Now you are saying that, okay, given this board state, tell me the maximum number of moves I can make with this particular state. So hope you can see the exact same problem, and hence recursion. So let's say there is a function f that can answer this question, that given this board state, what is the maximum number of moves possible from this board state and with some knights and some pawns. So you can simply call that function f here and you will get the answer. What does that mean? Let's say this is the board state. You will again do the exact same thing. You will say, okay, what you have done here, you try to capture each of them and then check which is giving you the max result. So you'll do the same thing. From here, you will try to capture one by one. So let's say you first try to capture p1. So in that case, this is the board state that Alice will get, right? If you capture p4, this is the board state that Alice will get, and if you capture p2, this is the board state that Alice will get. And depending on let's say you again call this f here, because this is exact same problem with just reduced number of pawns. So you can rely on f to give you the best possible result. And once you get the best possible result, you can simply take the max across all of them, and that will be your optimal result for this particular board state. And once you figure out this, you can get this values for others as well. And once you have the values for all of them, you can just take the maximum to get the value here, right? So hope you can see the recursion here. So let's just look at it a bit more formally. So let's say at this state, Alice wants to capture P1, and let's say it takes A1 number of moves or A1 number of minimum moves to capture P1. Again, you should not waste cycles or waste moves here as per the problem statement. So in just A1 moves, you get to P1, and this is the board state that Bob will get. Similarly, you will try to expand this using the same trick, right? And after you expand this, let's say you get x1, right? So if you capture P1 first, the total number of moves that is made during the entire game is A1 plus x1. Similarly, if you capture P2, let's say you need A2 number of moves to capture P2, and to capture the rest of the things starting at Bob, that is f of this particular grid is coming as x2. So you need A2 plus x2 total number of moves, or rather A2 plus x2 total number of moves will be played during the entire game if Alice captures P2 first. Similarly, if Alice captures P3, you will have some A3 plus x3 and so on and so forth, and you simply take the maximum across all of them, and that will give you what is the best possible move that Alice can play. Let's say A1 plus x1 is the maximum. So what basically means that Alice will start from here and will first capture P1, whatever that state is, right? So if you want to solve for any of these board state, again you will do the same thing. Basically, you will try to capture each of these. Let's say in B1 moves, you are able to capture P1 starting at this particular K. In B2 moves, you are able to capture P4, and B3 moves, you are able to capture P2. And once you get a board state, f of that, let's say, is coming as y1, f of this is coming as y2, and f of this matrix is coming as y3. So what you have is, if you capture, or if Bob captures P1 first, in the game there will be total B1 plus y1 number of moves. Similarly, if Bob captures P4 first, total number of moves during the game would be B2 plus y2, and similarly B3 plus y3 if Bob decides to capture P2. And total number of, you can just simply take max across all of them, and that will be the move that Bob will play, right? So hope this entire recursion tree is clear. Now, if you have watched this to this point, I would encourage you to pause and try to at least come up with the pseudo code for this entire solution. No matter, you should not worry about the complexity part of the pseudocode, just try to code this out by yourself. So how would you exactly do this in action, or what does function f will contain? Function f will contain two things: what is the position of knight, and what are the position of pawns here. So basically, function f is taking this entire board. Instead of maintaining this 50 cross 50 board, you can simply maintain what is the position of knight and what are the position of pawns, because number of pawns and number of knights are very less compared to total number of squares in the board, right? So from this, you can either capture P1 or P2 or P3 or P4. Depending on which one to capture, you will again call f with the reduced or remaining pawns that you have. So if you try to just write this thing in a recursive function, this is how it will look like. You will have a k and a pawn. K denotes the position of the knight, so it has two things, x comma y. Basically, it's a pair of integer rather than a single integer. And pawns denote the array with array of positions of pawn that is remaining. So if pawn is empty, it means the board game ended, and you'll simply return 0. Otherwise, you will go and try to capture each of the pawn one by one. Depending on which pawn you capture, you will figure out what is the total number of moves that can be played after this pawn is captured. And remember, to capture this pawn, you need to make some moves, and that moves should be minimum possible moves. So let's say you have a function min move somewhere, I will not discuss. We'll worry about this min move function later. But let's say there's a function somewhere which will give you what is the minimum number of moves you can capture a pawn at some p dot x and p dot y from k dot x and k dot y. So this is the total number of moves that you will play during the entire game, given you try to capture this particular p first, and you will simply take maximum across all of them, and that will give you what is the maximum number of moves that can be played during the entire game if you make an optimal choice at this particular move, right? So given this, what is the overall time complexity of this entire recursion? Notice that we are doing memoization here to ensure that the same state doesn't get computed more than once. So one state will be computed exactly once, and hence the complexity would simply be number of states multiplied by what we are doing to calculate each of the state. So let's first figure out what you are doing to calculate each of the state. So what you're doing, you have a for loop here that goes over all the pawns. So let's say there are total p number of pawns. So this for loop will go up to order p time. And inside this, what you're doing, you are calling a function that will give you the minimum number of moves from a cell to a cell y. So let's assume that that function complexity is m to find the minimum number of moves. This m will come to later, but let's assume that that function is taking order m time to get us the minimum number of moves from a cell to a different cell. And finally, after that, you are doing some mathematical operation that is just order one time. So we can exclude that. And this is your overall thing that you are doing inside this function to compute a single state. Now, how many states are there? So total number of states would be number of different values of k and pawns with which we can call this particular function. So as we discussed, k is actually a pair x comma y, or rather a position in the cell. So number of different rows can be 50, right? And number of different column can also be 50, because it is 50 cross 50 board, right? So overall there are 50 cross 50 number of different values of k that is feasible. And how many different values of pawns are feasible? Again, it depends on how you are storing the pawn. So if you maintain something like this 2D array where this denotes x and this denotes y for all the remaining pawns, so in that case, this can take any value between 0 and 50. This can take any value between 0 and 50. This can take any value between 0 and 50. This can also take any value between 0 and 50, and so on and so forth. But the total number of different pawns here are still constant. So you can figure out this if you try to maintain this. What happens if you try to maintain this integers? But instead of doing that, what you can do is you can maintain a single array with a boolean which is 0 or 1, whether a particular pawn is captured in the previous moves or not. So if you do this pawn thing, you can maintain just 2 power p number of states, right? Basically there are p spaces, each space has either 0 or 1. So you simply can have 2 different values here, 2 different values here, 2 different values here, and all of them are independent. So 2 multiplied by 2 multiplied by 2 p number of times. So overall 2 power p states here. So if you do it naively, this is your overall time complexity of coding this entire thing out. Now this is very huge and will not pass the given time constraint. Why? 50 square is like 2.5 multiplied by 10 power 4, right? And similarly, if you sorry, it's basically this multiplied by this itself is very huge and will not fit, no matter what this particular thing is r. This entire thing itself will not fit in the given time constraint, because p is of the order 15 or 16, 15. So this 2 power 15 multiplied by this entire thing will not fit in the given time constraint. So you need to reduce your state, because even if you try to reduce what you are doing to calculate each of the state, that will not matter, because the number of state itself is very huge in this particular scenario. So you need to reduce this. So how to reduce the number of state? Would encourage you to pause and try to think for a moment by yourself. So there are two ways, right? Either you change your complete approach and say, okay, instead of maintaining, okay, this is my recurring problem that I am fighting for, I will have some other recurring problem that I will try to find an answer for. So that basically means you are completely changing your approach, which is harder. So let's think if you can reduce some of these without changing your approach itself. That is, you still want to maintain the state of the board, but can you maintain the entire board in less than this much state? And the answer here is yes. So this 2 power p you can't reduce further, because you need to understand, like previously it was like 50 power p or 50 cross 50 power p, but you reduce it to 2 power p by just simply saying that I will simply maintain 1 or 0 for each of the cell. Now this we will not be able to optimize. Can you optimize this? What does this denote? This denotes the position of the knight. Now if you try to store the position of the knight, you need 50 square, that is for sure. So what you're looking for is there a way to store the position of the knight without actually storing the exact cell? And the answer is yes. You can simply store what is the last pawn that you capture, because if you look at it, the position of the knight is simply the position of the last pawn that we capture. So if you capture this particular pawn, this is the position of the knight. Similarly, if you capture this particular pawn, this will be the new position of the knight. So what you can do is you can simply maintain an index in the pawn array itself. Basically, you can say that, okay, which pawn I have captured in the previous iteration. So instead of this 50 square, you can simply maintain a index I, which can go all the way from 0 to p. So overall complexity or updated complexity is now 2 power p multiplied by p square multiplied by m. Now this also this can pass the given time constraint depending on what m is, and we'll come to that in a moment. So let's just look at the updated pseudocode. The pseudocode would simply update, instead of maintaining a k, we'll simply maintain the index of the last pawn that we captured. And how to, like, notice that this way you can have the value of value of k for intermediate state easily, but initially k is at a different position altogether. Now how to tackle it, I would leave that as an exercise to you. You can I am very sure you will be able to get it if you try to think a bit more. So assuming that you can simply maintain an index to get the actual position of the knight, you can, inside the function itself, you can use this index to get the position of the knight, and rest of the things will stay the same. So hope you are clear that this, how to achieve this complexity. If you are not clear at this point, would encourage you to pause and try to think which part is not clear, and rewind and watch that section again, because the next part of the video will be focused on how to model this solution into the actual problem itself, because we were solving the smaller version of the problem, yet we haven't tackled the original problem now. So from this state, we need to there are two choices. Either you can just try to figure out what is the value of m here, but let's not go there, because m you can somehow figure out in just order one time. How, I would leave that in exercise, and we will disclose that towards the end of the video. So next, let's try to focus on original problem now. What was the original problem? Original problem was, given Alice is trying to maximize the sum, but Bob's intention is to minimize the sum. What does that mean? This means that the same when you give this particular position to Bob, Now Bob is not asking the same question. Alice was asking that, okay, given a board, tell me what is the maximum number of moves that I can make given this particular state. And Bob was also asking the same question, that given this board, tell me the maximum number of moves I can make given this state. But now Bob is asking a different question. Bob is saying that, okay, given this board state, how many minimum number of moves I can make during the entire game. So that will be the thing that I should play right now, right? So you don't have the exact same problem here, and hence the exact same recursion will not be applied. But you can model it in the same fashion. How? Would encourage you to pause and try to think at least for 10 minutes by yourself. So hope you thought about it. The solution lies in the fact that, okay, Bob is not thinking about maximum, but once Bob makes the move, at this point it's again Alice's turn, and Alice will talk about the same exact thing, or Alice will instead ask, okay, given this state, what is the maximum number of moves I can play? And this problem is exactly equal to the original problem as well. So there are some recursion thing that we can see here, but you need to somehow make sure that both Alice and Bob are playing the move, which is a bit harder. So you can simply say, okay, I have a function, this function, or let's say there is function f1 which will take in a board state and will give you what is the total maximum number of moves you can have in the entire game given this particular board state. And let's say you have a function f2 that will give you, given a board state, what is the maximum number of moves I can have for this particular board state, or what is the minimum number of moves I can have if I play optimally in this particular board state. So what you can do, when Alice will make the move, you can simply call f2 for these states, right, and get the value from f2. And once Bob is trying, like let's say you're trying to calculate f2, in f2 you can call f1, right, and that's it. You will be able to solve this entire thing in this exact same fashion. So let's look at it with a concrete example. At this state, let's say how does implementation of f1 look like? It will be exactly equal to what we have seen before. This is the exact implementation of f1. Now how would the implementation of f2 look like? f2 is exact same thing, but we are trying to minimize the number of moves that are played during the entire game. So instead of taking max, we will take min, right? That's the only change in f2, nothing else. So what we will do is we can call f1 for this board state, right? And for this one, what will f1 do? f1 will try out every possible move or every possible way to capture a pawn, and will simply call f2 for the remaining board state, right? So let's say while calling f2 you are getting x1, so f1 will simply take max across all of them, and that will be the answer for f1, right? Now what does f2 do? f2 will do exact same thing, but instead of taking max, it will take min, right? So f2 will also try every possible way to capture a pawn, and once it capture a pawn, it will simply call f1 to get what is the total or what is the maximum number of moves that could have been played starting this board state, because that's now Alice's turn and Alice want to maximize. So it will call f1 to get y1, y2, y3, and once it gets y1, y2, y3, it will simply do the sum with b1, b2, b3. Notice that this will not change. Why? Because this is the minimum number of moves. Now this y1 can be different from the previous y1. This y1 can be y1 dash, y2 dash, y3 dash, and so on and so forth. So you will call f1 for all of these. Whatever is the value, you will simply take minimum across all of this, and that will be your answer for x3. And you simply figure out the answer in similar way for other x to get the final answer for the original board state itself. Now how to code this entire thing? That all looks good in theory, but how to code this? Again, you can either maintain two different recursive function and call function 2 from function 1 and function 1 from function 2, the thing that is shown here, or you can simply maintain that in the same function with a different state. So what you can say is, okay, I have the same function f, I will maintain one more state here, and whenever, based on whether it is 0 or 1, I will either take max across all the steps, or I will take min across all of the steps, because that's the thing which is different in the two scenarios. Rest of the things are exactly similar. So this is exactly how the pseudocode would look like for the original problem itself. One more thing to note here is the initial value that you start for answer will also change based on whether Alice is playing the turn or Bob is playing the turn. Now what is the time complexity? Time complexity would still stay the same. Only thing is, number of states is now changed. There are twice as many states as there were before. So there were just these two things before, and there were some state. Now you will have, for each of the state, you either, it could be an Alice's turn or it could be Bob's turn. So there are twice as many states as there were before. So the complexity would simply be multiplied by 2, which is fine. You can simply ignore that as well. So complexity is still same. Now the very last question to answer is how to calculate the m efficiently, because if m is even 50, this will overflow the given time constraint. So you need to either reduce m to order 1 or order log n. Order log n will also not pass depending on how you code it, but the m should be very, the computation of m should be very small. So would encourage you to pause and try to think for a moment. Now what does m denotes? M denotes what is the minimum number of moves required to go from a cell C1 to a cell C2, right? So for example, if you are starting from here, let's say this is C1, to go to this cell you just need one move. To go to this cell you just need one move. To go to this cell you need one move. To go to this cell you need one move. Notice that we are talking about the minimum number of moves, not the maximum number of moves, because maximum number of moves can be infinity in theory, because you can simply keep going back and forth with the knight and waste moves there. So basically from here you can transition to these all things in one move. Now similarly, let's say from here you can again transition back to this one, or go to this one, or different other moves as well. So basically this is a graph. So from a node you can go to some of the nodes. From those nodes you can again come back to this node, or maybe go back to some other nodes or some other nodes. So this is a complete graph in itself. And what you want the shortest path between all the pair. So if you think about an algorithm like Bellman-Ford or other shortest path algorithm, you can apply all of those, but the property that is interesting in this graph is each edge is of weight 1, or this is an equiweighted graph. And in this case basically you can simply use a BFS that would give you the best possible answer, right? If the weights are not equal, then only you will think about, okay, should I go in this direction if I can discover this right now, or should I go to someone else? But if the weights are equal, no matter which one you choose next, everyone will lead you to the same distance of the next cell if it is reachable. So what we can do, we can start a BFS from this particular cell and explore and try to go to all possible reachable cells in this particular grid, and that will give us what is the minimum distance from this cell to every node or every cell in this particular grid. Now what is the time complexity of figuring out this? Basically you can simply visit each cell exactly once. So overall time complexity is order 50 square, or order size of grid, to figure out what is the minimum distance from this cell to all the cells in the grid. But this C1 is not fixed. This C1 can be anything, right? So what you can do, you can repeat the exact same algorithm for all the cells, that is 50 square cells, to get what is the minimum distance from any C1 to any C2. And in just this much time, you will be able to figure out that. And once you figure out that, you can simply store it in a 4-dimensional matrix or however you want to store, and you can answer this question in just order 1 time afterwards. So this order n will be order 1 and will be removed from the time complexity, and this will be your overall time complexity, which will fit in the given time constraint. So would encourage you to pause and try to code and get it accepted as well. Next, we will be looking at the code. Again, I intentionally left a few pieces for you to think about it, so would strongly encourage you to think and code it out by yourself. So the code is exactly what we discussed. We first figured out what is the minimum number of moves from some C1 to C2 for all C1 and C2. So what we do, we go to every cell one by one. Starting from this cell, we figure out what is the minimum distance to all of the cells. So we call a function expand, which simply do a BFS to get what is the minimum distance from this cell to all other cells. So we start our BFS from xy with a distance of 0, and as and when we are discovering a new cell, we simply increment the distance to 1 based from the previous node that we discovered, that discovered the current node, right? And because of this visited array, every node will visit exactly once, so this entire algorithm would run in simply order 50 square, and we will be doing this for order 50 square number of nodes. So overall complexity is order 50 to the power 4, which is fine. Now next part of the algorithm is to figure out the moves. So it is Alice's turn, and notice that you need to figure out you need to somehow maintain what is the position of the knight. So instead of, if I just go back here, instead of k, we replaced k with a index here, right? So that the complexity can be reduced. But the initial value of k is something that is dynamic. So what we have done is we simply pushed one more pawn at the end and said that that is the knight, and we will simply capture it in the first go itself. Basically, we are saying the last position of this array is where the knight lies, and after this, we will just point this index to the last position for the very first iteration, and everything else will simply follow through the previous iterations in the previous way that we have discussed. So this particular function is exactly equal to the function that is shown here. So hope this entire thing is clear. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.